Hello, everyone. This is the last week. I hope you enjoy my class so far. And I really enjoy teaching you online, although I didn't meet you in person. I met some of you on the online office hours, but not all of you. So I hope you like my class and recommend it to many other students. So let's start this week material. So this is Unit 9, Part 3, Multiple Linear Regression, Bayesian Approach. We covered the simple linear regression, which has only one explanatory variable and one response variable. But now we need to cover many explanatory variables and one response variable. And then I will apply the idea on the house price data that you are familiar with. And then I will talk about what is next. So in multiple linear regression, we have many variables. One of them is called the response variable, and the others are explanatory variables. And the researcher thinks that these explanatory variables have some impact on this response variable. They can explain the variability in the response variable. And then after we analyze the data, we will see which one has some impact on the response and which one doesn't have any impact on the response by testing the betas are these or not, by testing these guys. Because if we tested this one and we found beta 1 is not significant, it means X1 has no impact on Y. It means X1 doesn't explain any variability in Y or significant variability in Y. So what is the meaning of beta 0? Beta 0 is the average of the response variable Y when all the explanatory variables are 0. If you plug in X1 is 0, X2 is 0, up to XP is 0, you will find Y equal beta 0 on average. And what is the meaning of beta J in general, like beta 1, beta 2, and so on up to beta P? Beta J is the change in Y on average when Xj changed by 1 unit and all the other explanatory variables are constant. When all the other explanatory variables are constant and we change it only Xj by 1 unit, why will it change on average by beta J unit? You need to define the likelihood or the data distribution, whatever you are working with, frequency approach or Bayesian approach. Let's assume the data follows normal distribution. Which data? Do you mean the explanatory variables or the response variable? I mean the explanatory variable. The response variable. I mean the response variable follows normal distribution. So each value, each observed value, yi, given beta and sigma square and x's, follows normal distribution with mean this one and sigma square. So can the response variable follow some other distribution? It can follow some other distribution. Maybe y follows Poisson distribution if it is count data. Maybe y follows beta distribution, maybe inverse gamma distribution, log normal distribution, or any other distribution. But the very common one is if y is continuous, most probably it will follow normal distribution. What about the priors? Again, the model or the data distribution is y, the response variable or the vector of the observed values given x's and beta and sigma square follows multivariate normal with mean x beta and variance covariance matrix sigma square I. This one means we assume x's are independent. There is no correlation between x's. And each variable has the same variability, or each variable has the same variability sigma square, or each observed value randomly selected from the same from a distribution has the same variable sigma square. What about the priors? You can use the prior distribution for beta proportional to 1. It means you have no information about the parameters beta. Also, you can use normal distribution for each parameter. You can use probability of beta, beta j, is normal distribution with mean 0 because I don't know beta j is negative or positive, and sigma square, and I use a very big value for sigma square. Why big value for sigma square? Because big value means big variability, means less precision. It means I have no information on beta j. So I can use the mean is 0 because I don't know it is positive or negative. And I use sigma square big because I have no information about it is close to 0 or not. So with j, for j equal 0, 1 up to number of parameters, P. Also, I need to assign a prior distribution for sigma square. Let's assign inverse gamma with A and B. I changed alpha and beta that we use many times. I changed the notation to be alpha and beta because we have beta in our parameter. So I don't like you to get confused. So I used A and B rather than using alpha and beta. So now we define the data distribution, so we can find the likelihood, and I define the prior distributions. Can I use those guys to find the joint posterior distribution? You can do it. Can I find the marginal posterior distribution for each parameter? This one is not easy because it has many integrations. So, and maybe as there is no closed form, maybe you will not be able to find the marginal posterior distribution. So it's better to work with the conditional posterior distributions for the parameters. So how do I find the conditional posterior distribution? It's very simple. The conditional posterior distribution of beta given these parameter and those guys proportional to the multiplication of the likelihood by the prior distribution of beta. Where is the prior distribution of sigma square? Because this one is a function of beta, and I assume sigma square is constant, so I do not multiply by probability of sigma square. So this one times this one. If I use this one equal 1, if I use the prior distribution of beta proportional to 1, so this one is the posterior distribution of beta proportional to the likelihood. So now let's simplify this one. Multiply y transpose times y transpose times the negative x beta, and so on. You get this one. And you will get rid of y transpose times y because this one is constant. So I keep those guys because are a function of beta. And then I will add the identity matrix between x and beta. Identity matrix can be written as x transpose x inverse times x transpose x because this one is I. And this one is beta hat. So I would simplify this one to get this one by the end. When I get this one, you can get this one from this one using the integrals by the complete square. So this one is a kernel of what? This one actually is a kernel of multivariate normal with mean beta hat, and the variable is beta, and this one is the variance covariance matrix. So this is the probability or the conditional posterior distribution of beta given sigma square and x and y follows multivariate normal distribution with mean beta hat and variance covariance matrix sigma square times x transpose x inverse. This is conditional posterior distribution because it depends on sigma square. If it doesn't depend on sigma square, it means it is marginal posterior distribution of beta because it depends on sigma square. So this is conditional posterior distribution of beta. So let's find the conditional posterior distribution of sigma square. The conditional posterior distribution of sigma square proportional to the likelihood times the prior distribution of sigma square. Why you do not multiply by the probability of pi? Because this one is a function of sigma square and pi, so we consider pi as a constant. So when you multiply the prior distribution of sigma square, which is inverse gamma, I use the kernel only. I use only the kernel of the inverse gamma. And this is the likelihood. So when you multiply the likelihood by the kernel distribution, of the inverse gamma. This one with this one gave me this one. And this one with this one gave me this one. When you look at this one actually is a kernel of inverse gamma. The alpha star is this one, n divided by 2 plus a, or a plus n divided by n plus n divided by 2. And the beta distribution is b plus SSE. What is SSE? SSE is this part. This is the sum square due to error, actually. So you can write SSE or you can write this one. It's up to you. So now we find the conditional posterior distribution of sigma square as inverse gamma with alpha star a plus n divided by 2 and beta star is b plus SSE divided by 2. I can use these two conditional posterior distribution to find or to generate a random sample from the marginal posterior distributions using the Gibbs sampler method that we have covered before. So let's practice on this real data set, the house price data by the Bayesian approach. So we worked with this data before, but we worked with the house price as the response, and the house size is the explanatory variable. But now we have many explanatory variables. X1, the taxes. X2 is the number of bedrooms. X3 is the number of bases. X4 is the house size. X5 is the lot size. Now we have 5 explanatory variables and 1 response. And we need to know which explanatory variable has some impact on the response and which one doesn't have any impact on the response variable Y using Bayesian approach. So again, let's define the likelihood for this example. We have 5 explanatory variables, x1 up to x5. So each observed value yi follows normal distribution with mean mu I, which is this part, and sigma squared. So x1 is the taxes, x2 is bedrooms, x3 is bases, x5 is house size, x4 is house size, x5 is lot size for the house number I. What about the prior distributions? Let's assign normal distribution with mean 0 and sigma square is 100 squared. So 10,000. It means I have no information about beta J. But if there is some information available, I can make the normal distribution is not 0 and big value for sigma square. I can use this previous data to make the prior distribution for the parameters. I will assign the same prior distribution for all the parameters, beta 0, beta 1, beta 2, beta 3, beta 4, beta 5. And I will assign a prior distribution for sigma square, inverse gamma, with alpha is 0.01, beta 0.01. So it looks like this one is non-informative prior for sigma square, non-informative prior for beta J. Now let's run the code in the file RLab multilinear regression. I recorded the video for this one, so please go to this one. And before you go to this one and run the analysis together to find which variable has some impact on the response and which variable doesn't have impact on the response variable using Bayesian approach. After we finish this one, I will go over the generalized linear model. In generalized linear model, Y doesn't follow normal distribution, it follows something else. So after I finish this one, I will go over generalized linear model. Thank you so much and see you in a few minutes on the recorded video for the multilinear regression using Jagg's function. Thank you so much.